Hi guys, in today's video we're going to be taking a look at the moment of inertia of an extended object, and then we're going to see how that relates to that object's energy. So the first things first, we want to decide what it means when we say an object has a moment of inertia. And basically this is a quantity which is going to tell you the object's resistance to rotation or resistance to changes in rotation. So basically we want to think about mass for a single particle. The moment of inertia is kind of like the analog, the rotational analog of mass. So if we have a particle and it's more massive, it's going to be harder to accelerate. So it's harder to change the motion of an object which has more mass. So similarly, an object which has a larger moment of inertia, it's going to be harder to change its rotation. So in terms of the precise definition, we can find the moment of inertia for any extended object. And this will be defined with respect to some axes. So we choose our axes. And then the moment of inertia about that axis is going to be, we're going to sum over all of the masses, so all of the particles we have in our system, and each mass will be multiplied by its position vector squared. So this is sort of your definition. You can extend this to the continuous case of a rigid body. But for now, we just want to know basically the idea, how we would get it in principle. And a lot of times you guys will be given simple enough objects like spheres or disks, and you'll sort of know the moment of inertia of those objects. And so this is sort of our definition here. And now we're going to be able to use this in terms of defining, splitting up our kinetic energy in slightly a different manner. So the basic idea here is that an object which is undergoing both translational and rotational motion, so for instance, if we have a wheel on a car, perhaps this car itself is moving to the right. So maybe this wheel has some translational velocity, so some linear velocity to the right, but the wheel itself is also spinning about its own axis. So the wheel also has some rotational motion. So we see now we can have these scenarios where we have both rotational and translational motion. And in that case, our kinetic energy term, it's going to be much easier for us to think about this by splitting it up into a kinetic energy term due to the translational motion, and then another one due to the rotation. So in this case, we're basically going to split up our kinetic energy to kinetic energy translation plus kinetic energy rotation. So these are just two terms, and our translational kinetic energy term is going to be the same form that we've been working with. So this one will just be 1/2 mass times the linear velocity squared. So nothing really changes here. But now if this is also rotating about its own axis, we actually have extra kinetic energy just due to the rotation itself. And so now we sort of need to write the form of that extra kinetic energy, which comes into play. And that is of the form 1/2 I. So you see we have an I instead of a mass, and then omega squared. So you'll see this is really directly analogous to our translational kinetic energy. It's just instead of mass we have I, and instead of velocity we have angular velocity. So in general we want to make sure we split up our motion and see does it have rotational motion and translational, and if it does we need to add those together to get our total kinetic energy. So let's look at our problem statement for today, and that reads as follows. Two metal disks, one with radius R1 equals 2.5 centimeters and mass M1 equals 0.8 kilograms, and the other radius R2 equals 5 centimeters and mass M2 equals 1.6 kilograms, are welded together and mounted on a frictionless axis through their common center. A light string is wrapped around the edge of the smaller disk, and a 1.5 kilogram block is suspended from the free end of the string. If the block is released from rest at a distance of 2 meters above the floor, what is the speed just before it strikes the floor? And repeat this calculation if the string were wrapped around the edge of the larger disk instead. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here. And so in this case, we're sort of looking head on at these disks. So these will be rotating in this fashion as this block descends. And to the block is going to fall 2 meters. And we want to find the velocity of that block after those 2 meters. And so the first thing we want to note is, of course, there will be rotational motion from both of these disks rotating this way. So we can go ahead and just start off by finding the moment of inertia of this system, because we know that's going to come into play. So the system here basically, again, looking head on, we have these disks, and they're going to rotate in this fashion, for instance. And so they'll be rotating here. And so we want to find the I, so the moment of inertia, of both of these disks, right? We're not concerned with either individually. We're really concerned with this whole system is going to be rotating. And so in this case, that's actually easy enough. That really is just saying the total moment of inertia of the system of both welded together disks is going to be equal just to I1 plus I2. And so here 1 is just the smaller disk, 2 is the bigger one. And so the reason this is you can recall back to the form of the moment of inertia. There you just sum over all of the particles in your system. You multiply their mass times their position vector squared. And so in this case then we see that that sum can just split up separately for each of our disks. So it's sort of this simple. And we know, of course, I1. This is just the moment of inertia for disk 1. For a disk, we know the form of the moment of inertia is going to be 1/2 m1 r1 squared. So we can do similarly for I2. It's the same form because it's the same shape, but now we have mass 2 and radius 2 squared. So these are quantities you guys can solve for directly. Just plug in your known quantities. Plug those in here. You can plug that into this equation, and then we can solve directly for the total moment of inertia. So go ahead and follow along in your solutions, and you should get to an answer of 2.25 times 10 to the negative 3, and the units should be kilograms meters squared. So I'm going to go ahead and box this because this is an important result which we will be using. And so that's to say that the moment of inertia of both of these disks as they rotate, this whole system, is going to be 2.25 times 10 to the minus 3. So we'll go ahead and use that in a second, but now we want to look back to our system. And so we see throughout this whole motion in the system, the only force that's acting is going to be gravity. That's really the only thing doing work here. And so therefore, we know that our total mechanical energy is going to be conserved. So we can write energy initial must be equal to energy final. So that's to say whatever mechanical energy we start with cannot change the total value, right? We can change forms, but we're not going to change the total energy present. So let's go ahead and just write down both of these sides. So our initial energy, we should see, is really just the mass of the block times gravity times height. So this is just to say we have some potential energy from this block. There's no other energy terms to worry about at the beginning. And so that is entirely going to get transferred into some kinetic energy final. So we see as this block reaches the ground, there's no more potential energy because we've defined the ground to be our 0 point. And then now that there is going to be rotational kinetic energy and some translational. So this kinetic energy final is not going to be in quite as simple a form as before. We have to take into account both the translational kinetic energy down here from the block and also the energy that amounts to these two disks rotating. So this kinetic energy final then, let's go ahead and just write that whole term out. We know that should be equal to 1 part from the translational energy. So that would just be 1/2 mass of the block times velocity final squared, right? This V final is of the block. So this is our translational energy from the block, but we also have this rotational energy from these disks. And we know the form there is going to be 1/2 I total because it's from both of the disks. And then omega, we'll call this omega final squared. So that's just to say when this block reaches the ground, these will be rotating with some omega. So at this point, we're almost there. We know mass times gravity times height equals this side of the equation. And so all we really want to do now is get this down into one unknown. Right? At the moment, we don't know velocity final. That's actually what we want. And we also don't know the angular velocity. So all we need to do is relate linear and angular velocity. And you guys will remember we've done that, for instance, in the last video. We know that the relation for these rotating objects is just going to be V final is going to be omega final times the radius. And so in this case, we can just use this, plug that into this equation, but we have to be careful about which radius we use at this point, right? We have 2 radiuses to worry about for each disk. And so at this point, we need to think about which one ties together the final velocity of the block. And so in this case, the block we see is connected to a string, and that is directly connected to disk 1. So this radius here, in this instance, we have to use radius 1. So we're not going to use radius 2 because the velocity is equal to omega times this radius, the one which the string is tied on. So this is our relation, so being careful to use radius 1 instead. We can solve this for omega, plug that in here, and then solve this relation for V final. So go ahead and please follow along in the solutions at home. There's a couple steps here, but you should be able to get then directly to your velocity final, and it turns out that that should be This should be equal to 3.4 meters per second. So I'm going to go ahead and box this. So that's to say our velocity final will be 3.4 meters per second as this block reaches the ground. And so we have one extra part which will be very quick to solve, but they ask us what happens if instead this is tied around the larger disk. So that's to say that instead maybe we have the scenario where this block is actually hanging from disk 2. They're both still welded together. So everything here is going to be the same. We still have the same system. And the only thing that's going to change is this step right down here, right? So in our second scenario, we really have, and this is for part B. Maybe I'll write this here as part B. For part B, we just have to change this part right here, right? Because our final velocity is now tied to disk 2 and not disk 1. So our velocity final is now going to be omega final, but this will be multiplied by radius 2 instead of radius 1. So we can do the same steps, plug this in up here, and solve for final velocity. And we should get final velocity, in this case, equal to 4.95 meters per second. And so that's to say if the string is tied around disk 2 instead, we get a larger velocity of 4.95 meters per second. Okay, so let's go ahead and review how we did this problem. We first solved for the moment of inertia for the system of disks. Then we noted that we only have the force of gravity acting, so mechanical energy is conserved. We equated our initial and final energies, noting that in the final scenario we have both linear kinetic energy from the translational motion of the block and also rotational kinetic energy from the rotation of the disks. So we solved this then for our final velocity, given that the string was tied around block 1 and block 2 separately. Okay, so I hope this video was helpful, and I hope you guys sort of understand now a little more about moment of inertia and about how to split up your kinetic energy into rotation and translation. So if you guys have any comments about this video or any of the videos here, please leave those on the comments link, which should be to the right of the video link. And thanks for watching.